M2? Okay, all right. All right, so let me start with a brief introduction of our speaker today, Miss Anam Toha. Anam did her master's in physics from the University of Burgundy, France, and is currently doing her internship at Johannes Gutenberg University, Germany. She's associated with CASPEr experiment, which aims to search for dark matter based on dark matter-driven spin precision. So I welcome Anam to our Physics General Club on behalf of the Physics General Club organizing committee, and we also thank you. We also thank Anam for agreeing to our request to deliver a talk today. So with that, let me welcome Anam and let's listen to her talk.
Okay, so good evening from Europe and good morning from the US. So let me share my screen. So can you all see my screen?
Yep.
Okay. So it's visible?
Yeah.
Yeah.
Okay. So good morning, everyone. My name is Anam Toha, and I'm currently doing my master's in Université de Bourgogne-Franche-Comté, Dijon, France. And I'm currently associated with Helmholtz Institute of Mainz in Johannes Gutenberg University in Germany. And my internship is on the cosmic axion spin precision experiment, a dark matter search with nuclear magnetic resonance under the supervision of Professor Dimitri Butker and Dr. Hendrik Baker. So here I have shown that what is CASPEr and what is CASPEr gradient. So CASPEr is divided into two parts, that is CASPEr electric and CASPEr wind. So CASPEr wind has now a new name, that is CASPEr gradient. So as axions and axion-like particles have several predicted couplings to the standard model of particles. So CASPEr is a multifarious research program, searches for spin precision driven by axion-like particles. So with those coupling using NMR method, with those coupling, there is a induced term in a nuclear Hamiltonian, which I have shown here. So this is the strength of the coupling, nuclear coupling strength. This is the gradient of the axion field, and this is the spin operator. Here I have shown the graph of the experimental reach of the CASPEr gradient. So on the x-axis, you can see that there is a mass of axion-like particles in electron volt. And on y-axis, you can see that there is a coupling strength in giga electron volt inverse. And this is for axion-like particle Compton frequency. So the green part include the excluded part for the astrophysical observations, and the red part and the orange part shows different sensitivities, projections of the experiment at different fields, and phase 2 represents the sensitivity, higher sensitivity of the experiment. So, and this part shows the CASPEr Zulf, that is zero ultra low field. This is the sensitivity of this experiment. So first of all, describing about CASPEr and CASPEr wind or CASPEr electric, I will first of all show you some basics about nuclear magnetic resonance, that what is nuclear magnetic resonance. So it is a physical phenomena in which a magnetic field is perturbed by an oscillating magnet. Nuclei is in a strong magnetic field is perturbed by a weak oscillating magnetic field. So the response to this phenomena is the production of an electromagnetic signal with the frequency characteristics of the magnetic field at the nucleus. So the principle of the NMR involves three steps. So the first step is the polarization of the magnetic nuclear spins in an applied constant magnetic field. The second step is that this polarization of the magnetic nuclear spins by a weak oscillating magnetic field referred to as a radio frequency pulse. And third is precision usually occurs at Larmor frequency. So this is the figure of the Zeeman splitting at nucleons nuclei spin half. So this is the energy difference between the two energy levels, which is given by this, where gamma is the gyromagnetic ratio and B naught is the constant applied magnetic field. So here I have introduced some basics about CASPEr electric, which is going in Boston University. So what is CASPEr electric? CASPEr electric is related to the Axion-Gillion coupling. So due to this, there a term induces which is called nuclear electron dipole moment, which is given by this equation, where this term represents the strength of coupling strength. And the major difference between the CASPEr electric and CASPEr wind is that CASPEr electric is using a static electric field that is applied perpendicularly to the linear leading magnetic field. So as in CASPEr gradient, B naught is tuned to a tuned for at Larmor frequency for resonance. So if the resonance occurs, the axions induce the electric dipole moment, which oscillates at the Larmor frequency. So this is also the graph of the experimental reach for CASPEr electric, where different regions show different sensitivities of the experiment. And here you can see that on x-axis there is an axion mass, and on y-axis there is an axion coupling strength. So this green band shows the excluded part by the astrophysical observations, and this gray dash line is the vertical dash line, which represents the mass and the frequency corresponding to the axions generated by symmetry breaking at the Planck scale. So this is all about the graph. The more information about the graph you can see at the reference of the paper. So here I have posted a picture of our Faraday lab. That is, it is in our mains institute at Almos Institute, and this is our magnet. And so this is the part, this is the setup for our CASPEr gradient in which I'm currently doing my internship. So in CASPEr gradient, a sample of nuclear spins is placed in a magnetic field, which is tunable to a wide range of Larmor frequencies. When it is equal to the Compton frequency of axion, then a transverse magnetization will be built up, which we intend to detect using SQUIDs. So in our experiment, the range of our magnetic field is about 0 to 0.1 Tesla, and the range of our frequency is about 0 to 4.5 megahertz for protons. So this is our gradient coil, which is inserted with VTI inside our magnet. So this is the zoom version of our gradient coil. This is our gradiometer. So what is gradient coil? So in order to characterize the spin response to a magnetic field as needed for axion-like particles, a magnetic field is needed to be applied to the sample in X, Y, and Z directions. So for this, we have a coil of stacks which apply magnetic field in X, Y, and Z direction. And this coil of stack contain two saddle coil pairs and one Helmholtz pair. So this is our zoom, and this is our gradiometer. So currently I'm working on SQUIDs. So this I have shown some basics for superconducting quantum interference devices, as SQUIDs is a very sensitive magnetometer used to measure very subtle magnetic fields containing two Josephson junctions. So on the left, I have put a picture of a DC SQUIDs. So DC SQUIDs contain two Josephson junctions connected in parallel in a superconducting loop. When a current I is applied to the superconducting loop, that it is divided equally in the two branches. So if we apply some external magnetic field, then a screening current will be induced in the branches, which will create the magnetization opposing the applied magnetic flux. So the screening current will be same as in the direction of I in one of the branches, and will be opposite to the in another branches to the direction of I. So as soon as the current in either of the branches reaches the critical current, then a voltage will be appear across the SQUIDs. So this is the electrical schematic of our SQUID. So this is the IB current, which is the bias current, and this is I naught, which is the critical current of the squids, and phi is the flux threading to the squids, and V it's the voltage response to the squids. So this is our squids and it is feedback electronics. So as you can see that this is phi B couples flux to the squids through the gradiometer, and phi X couples flux directly to the squids for tests independent of the gradiometer. So in the future, we are planning to put our sample in the gradiometer to do NMR. So this is our gradiometer, and this is the simulation of the magnetic fields at different certain currents, and the different color shows different magnetic field, strength of different magnetic field. So here I have shown the IB curve of the squid. So as you can see, there are two curves. Blue curve shows the input curve and orange part shows the output curve. So below the critical current, there will be a superconducting region, and it can be shown by the flat region. And above the critical current, there will be a normal conducting region, which can be shown by this slopy region. This is the phi B curve of the squids. So phi B curve of the squids is periodic in nature. And as I have explained in my above slide, that orange part includes the shows the output wave, and blue part shows the input wave. So this is the point where the change of flux switches direction, which is equal to 1 flux quanta. So now if the applied magnetic flux, suppose if the applied magnetic flux is increased, and it is increased up to phi naught by 2. So as we know that in a superconducting loop, there must be an integral multiple of flux quanta. So instead of screening the flux, the squids will now to prefer to increase it up to phi naught. So the current will flow in opposite direction, opposing the difference between the admitted flux and the uh, applied flux of which is creating the difference of field over phi naught by 2. So current will flow in opposite direction and will decrease as the magnetic field increases, and it will become 0 when it will the flux becomes phi naught. So in this way we obtain a periodic curve of the squids. So as soon if the input current is more than the critical current of the squids, so the squids will always operate in resistive mode. So this is the phi B curve of the squid. That's why we observe a periodic nature of our phi B curve. This is, I have shown the calculation of the magnetic feedback sensitivity, which I have calculated from the phi B curve. So from the previous slide, as you can see that there is one change of flux quanta. This is equal to 1 flux quanta. So I have calculated the span of it, and then I have calculated the slope of the current input. And from these two input terms, I have calculated the feedback sensitivity, which comes out to be 10.95 into 10 to the power 3 phi naught by ampere. Here I have shown the simplified schematic of a direct coupled flux lock loop, that is FLL of a DC squid. So what is FLL? So as I have explained in my previous slide that the phi B curve of the squid is periodic in nature. So in order to linearize the V phi characteristics, we need FLL mode. So in FLL mode, the voltage output is first amplified, then it is integrated, then it is fed back through a resistor RF through a feedback coil, which is magnetically coupled to the squids. So in this way, the flux inside the squid remains constant, and in this way, the voltage output depends linearly on the flux of the squids. So here, once again, I have put the picture of the gradient coil because I have done the experiment with gradient coil and without gradient coil inside the magnet. So as I have said in my previous slide that our gradient coil is the stack of coils which applies magnetic field in X, Y, and Z direction, containing 2 saddle coil pairs and 1 Helmholtz pair. So I have compared the data at 0 Gauss with and without gradient coil and this is the spectrum, which is an average for 10 measurements. So as you can see that magnetic field at 0 Gauss with gradient coil, the spectrum is much more noisy as compared to the magnetic field at 0 Gauss without gradient coil. So this is due to the Johnson noise, which is created by our gradient coil, as the Johnson noise is the noise created by the thermal agitations of the charge carrier inside an electrical conductor. So that's why we observe more noisy spectrum as compared without gradient coil. And I have compared my magnetic feedback sensitivity with calculated and the specified value with the Magnicon, that is the company which have calculated the feedback sensitivity at different feedback. So at 5B and 5X you can see my calculated value and the specified values. So the values at 5B is not that much comparable, as because our setup is not that much accurate as compared to the company Magnicon. And one more thing is that we have done at different feedbacks, so that's why also we have different uh, there's a large difference in our values. So that's why we got but at 5x we got some comparable values of magnetic feedback sensitivity. So currently I'm working on the Johnson noise prediction. I'm working on the geometry of our gradient coil. So I have calculated the magnetic spectral density, which is given by this equation, where Kb is the Boltzmann constant, T is the temperature, R is the resistance, N is the number of turns in the coil, and nu is the frequency. So the predicted spectrum will be of linear shape on the log scale. So this is for flat coils, but I'm currently working on our gradient coil. So our gradient coil has different geometry, as it contains two saddle coil pairs and one Helmholtz. So hopefully in 1 week or 2 weeks, I will calculate the exact value of the Johnson noise prediction due to the geometry of our gradient coil. So this is the data without gradient coil. I have calculated at different magnetic fields at 0 Gauss, at 50 Gauss, at 100 Gauss, at 500 Gauss, and at 1 kilo Gauss. So all you can see that as the magnetic field increases, there is much more noise in the spectrum of our data. So this is due to the fact that this noise is created because as the magnetic field increases, SQUIDs observes more measures more large change in flux. So this large change in flux is due to our vibrations at the mechanical vibrations or setups, and which appears at very low frequency. So that's why we observe much more noise at low frequency as the magnetic field increases. So here also I have calculated the data. This is our data by Magnicon at a different frequency range, and my data and the data by Magnicon is comparable with these frequency ranges. So conclusion at last, I will say that Axion and Axion-like particles are well-motivated dark matter candidates. Data at magnetic field 0 Gauss is more noisy with gradient coil than without it because of Johnson noise created by gradient coil. At different higher magnetic fields, we see more noise. As the magnetic field increases, SQUIDs measures more noise. So in future, CASPEr gradient will acquire the NMR spectrum with hyperpolarized xenon. And the experiment also aims to determine the spin noise spectrum of various molecular species. So this is our collaboration of mains at JJU, and this is our collaboration with CASPEr Electric at Boston University. So we in Germany we are doing work on CASPEr gradient, and in Boston University people are working on Boston on CASPEr Electric, and this is my supervisor, Professor Dimitri Butker. So thank you all for your patience, and thank you.
Thanks a lot, Anam, for giving this amazing talk. And now we are open for any discussion or any questions if you have. And we also have a quiz. Should I put the link in the quiz, or should we first go for the discussions?
Yeah, maybe let's have some discussions. Otherwise, the quiz will distract us. Thank you, Anam. Wow, you guys are doing very incredible stuff. Well, I'll ask some very basic questions, not very much and well-versed about this dark matter detection. Just a very basic question, like starting off, what is an axon and how come, I just like listen to so many of the buzz news around it. Many people say it's hypothesized, it may not be real, and of course there are some people who believe it's mostly gonna be, there are like other kind of dark matter
Yeah.
candidates like WIMPs and so forth. And so just take us from there, like what is an axon and how do we know it's actually real, and how come we can detect it as you guys are doing?
Yeah, you are right that axions are not we are not sure about axions, but this is a hypothetical particle which is means invented to just solve the CP problem. So that is a spin zero bosons, but as I'm not from a higher energy field, so I don't know much more about axions, or maybe some higher particle physicists can tell more about it. So only this thing I know, that we are not confirmed about axions, that axions really exist. We are just doing means experiment that maybe they exist or maybe not.
Okay. So just a follow-up question on that, like, so from some of, like, I've just searched some videos and and listened to many people talking about this. So people are saying like many dark matter doesn't interact with baryonic matter, and another issue is that, okay, if you are having an experiment where it's like weakly interacting via this NMR, like what signal are you looking for in the experiment to say, this is an axion, we found it? Is like, yeah, I'm not sure, maybe I got lost in the details of the how the experiment is set up, but like what
Yeah.
signal would tell you that, oh, okay, we've found it now, or we haven't found it?
Yeah, we, as I've told that we have some frequency range for 0 to 4.5 megahertz, and we are founding the signals which will help the NMR community to detect for dark matter. So this will be more, you can see more about the sensitivity of quantum sensitivity of the CASPEr gradient. There is a paper, so you can get more information about it. So just we are helping the NMR community.
Oh, okay, I see.
So that's
Oh, yeah, you mentioned it's a collaboration. Okay, I see. Okay, thank you for that.
I would like to just ask some follow-up questions.
Yeah, sure.
Fatima already took up two of my questions, but thank you. So one, this hypothetical, what we know about this hypothetical particle is that it's chargeless, and that's why to see its interaction, you are approaching it through its interaction of magnetic field, right?
Yeah, we are working on the gradient of the magnetic field.
And what, so, and like you mentioned that you are trying to, so when the interaction, when the axion interacts, you will have some signal corresponding to frequency line between the range you mentioned.
Yeah.
So what explains that the frequency is going to be in that range and not in some other range?
Frequency in that range.
So you have mentioned that it will give you between 0 and 0.5 megahertz. Did you say that?
Yeah, megahertz for protons. Yeah,
Yeah,
because
so
we observe NMR signal at this frequency range, and we have a team. So different members are working. That my team, there is one another my team member who is working on this NMR, and I am particularly working on the SQUIDs. So I can only tell you more about the SQUIDs part. But I only know about that at this frequency range we observe an NMR signal. There is a peak in our NMR signal, and that's we got. So yes, we got an NMR signal. So
Yeah.
I know
okay.
about it.
Yeah,
And
no, it makes sense now because it's like, just to say Kushi, it's like a very huge collaboration. So
Yeah,
everybody is doing
yeah,
a section of the big experiment. And so when they collect the data
yeah,
from the NMR signal, they will send it to another team and they would analyze and uh, remove the noise and do
yeah,
other things
same thing.
to,
Because it's a
yeah.
very huge collaboration, and I'm just a small part of that collaboration.
Wow. It's now I see it's better to be a theorist. I'm just kidding. Yeah.
uh-huh.
Um,
Okay, so one more question.
Yes.
On the picture that you have on the screen, where you have mentioned that the green colored shaded region is the astrophysical region, which is not included in this detection procedure, correct?
Yeah, correct.
And so that is the supernova 1987A.
Yeah.
And why is that excluded? Or maybe like I don't see the connection between your work and the supernova.
Yeah,
And
my work is not this is I've just explained the basics, that what is the experimental reach for CASPEr gradient and what they are going to work, and what is their main aim. Their main aim is to occupy this. So my work is not in this. I have shown just I have taken the picture from the paper, and I have given the paper reference also. So they have worked very well about this. So my work is especially on SQUIDs. So there is no connection between this and my work. This is absolutely right.
okay, I understand.
Yeah.
Thank you.
just to ask you a question about your magnets there a little bit. So you have this Josephine junctions and
Yeah.
so I'm just curious to ask for to have it in superconductivity, don't you have to cool it or
Yeah, we have to pull it. Yeah, we
what
always fill it
temperature, right? Yeah.
at 4. We just fill it by liquid helium, and then we fill by liquid nitrogen also. So definitely we have to cool it. So we always do filling weekly
Mm.
for liquid helium and liquid nitrogen, and for this we
What
have
temperature?
at 4.2 Kelvin.
Wow. That you can have frostbites.
Yeah, so for this we have to go to another lab to collect the liquid helium. Then we just do filling. This is our DVAR for the liquid helium, and then in this way we do filling in this our cryostat, as you can see in the picture. So always we go to the another lab to collect our liquid helium from the DVAR and liquid nitrogen, and there are some safety rules and instructions that how we have to means how we have to handle that these cryogenic liquids. So that's why all there are very safety instructions for this, and therefore we have to be very careful during the filling.
Yeah, that's true.
Yeah.
I don't want to take up other people who may have questions. I just had one last. It's just a definition question. You in your conclusion you said 0G magnet. I didn't.
Yeah.
What does 0G mean?
Zero Gauss.
Magnetic field of zero.
Yeah, that data at magnetic field zero Gauss means we have
Oh,
we have a setup at which we just set our magnetic field, and then we just take the data from the SQUIDs electrical setup from where we set our magnetic field.
okay. Yeah, other people, you can just unmute yourself and comment. We're not very formal. It's just a discussion.
Mhm.
Yeah, Dave has something to say. Great talk.
So Anam, I have one question.
Yeah,
Okay, go
sure.
ahead.
So you're talking about some sample of nuclear spins that you have used. Can you tell what sample is it? Like,
Yeah,
uh,
it's methanol.
okay.
Mhm.
And any specific reason to pick this sample?
Yeah, because there's a 13 carbon, so that's why we always get NMR for 13 carbon. So now in future we are going to change our sample and we are going to use it with hyperpolarized xenon.
All right. Okay. All right. Thanks a lot.
I have a question. Your frequency range, you choose the frequency, usually you get some frequency range. Is it any relation with the mass of your particle, matters or antimatters? Like you have some mass, because of this, you have some particular range. If you change
What
yeah,
means mass?
because the mass of your usually your particles has different mass. So because of the mass, you might have a different frequency region.
Mm-hmm.
Is it anything relation? Because it's I know the stupid question.
Because of the mass, as you know that mass of means you mean to
Yeah,
say
like
that a frequency range for 0 to 4.5 megahertz.
yeah, it may be some relation with the mass.
No, no, no. I don't think so.
Okay.
Mhm.
Anam, you can ask us questions if people are quiet, or we'll go for the quiz. Let's get it.
I wanted to ask one question if, well, it's not very directly related to your talk, but
Yeah.
so axions are considered, so there is this charge parity problem which has been talked about, and it's said that axions are going to help us solve that charge parity problem. Will you be able to comment about it? I mean, I know you are not into this particle physics section, but I am a nuclear physicist, so I probably try to see it that way. So if you want to comment anything about the connection between charge parity problem and how axions can contribute to its solution.
Okay, I got your question, but the thing is, I have never studied about particle physics. I'm from the atomic physics, so mm, I can't comment on it that whether I know that there is a charge parity problem, some only basics about the higher energy physics that there is a charge parity. Maybe someone other can comment about it if someone is from particle physics, that how axions can solve the charge parity problem.
Yeah. So usually in our meetings, we have the faculty members for such cases, whereby because the Channel Club was actually designed for us to learn more, and it's very much not so formal. It's very an informal interaction that we read about things that are interesting. And the person maybe who knows more about it, they can present something just to get us started with the language and stuff. Yeah. But one thing that I know that is interesting on axons is that it is one of the it's one of the unique predictions of string theory. So if people can detect them, then that would bring so much reputation to string theory, because right now it's considered a super fancy math that has no relation to reality, or because they couldn't find supersymmetry, which was a big disappointment. So if they can find axions, I think they will be very excited. That's a different thing than what Kushi is asking about. And I think it's
Well,
important for us to understand what is actually the CP problem.
Yeah,
and-
because I think
I
it's
can,
sorry.
yeah, go ahead. No, go ahead. Otherwise, I was going to say I can try at least stating what the problem is.
Because it is a part of, I think, quantum chromodynamics. So I think who has well studied the QCD, he can explain more. If someone is in your group who has studied QCD, so he can explain more about that, how axions can solve the charge parity problems.
Like I can just comment on what I understand regarding this charge parity problem. So they call it as CP problem, and they say that a violation of charge parity symmetry is technically going to happen in strong interactions. But if you are observing, then no violation of charge parity symmetry has ever been seen in any experiment involving only strong interactions. Okay. So, and also like as per quantum chromodynamics, it is not like we don't know a specific reason to say that it should always be conserved. Yeah. So that's why like they want to understand if it has to be conserved all the time. If not, like there is some theory which explains that if there is a strong interaction, like if there is any experiment based on strong interactions only, we should see the charge parity violation, but we are not able to see it. So we need to know either it has to be always conserved, and if not, then why? Yeah, this is my understanding. And because axions are chargeless, then how is it going to even matter? It's like it is just going to behave like a neutrino, which is chargeless and just going to wiggle around with its tiny mass and just change the theories of physics. So yeah. Well, no worries. I was just, when I was reading your paper, I was like, what is axions? And then I came across this charge parity problem solution.
Yeah. Because I also have these questions regarding my mind. So, but the problem is that it's a huge collaboration. So my work is related to only SQUIDs. So that's why I can study for the interest, but I didn't get the time to read more about axions and about the charge parity problem.
I completely understand.
Nice.
I'm just a PhD student, and you can hear me complaining about time constraints all the time.
Can I ask one question?
Yeah, sure.
Okay, so the slide you are showing here, I can see different colors, right? So
Yeah.
I want to know the information you extract from the curve of blue and the pink. Let's say at 0 Gauss and at 1K. So why do you have to move at different magnetic field? Because you may not get, I mean, you have those noises at different magnetic field, right? So why don't you only rely on the curve that has less noise and you can obtain it at 0 Gauss? So
No, because in future we are planning to do with high magnetic field. So that's why we increase the magnetic field. We took the data at different magnetic field.
So what will be the advantage of that?
So the advantage of that is that as we increase the magnetic field, then we can get more information about our mechanical setup. That our mechanical setup is not that much perfect for the spin noise measurement yet, because now still there are some vibrations in our mechanical setup that are creating noise as we are going at higher magnetic fields, because that's the I according to my knowledge, I think so.
So Vigor, in order to overcome your mechanical setup, defects
Yeah,
of the mechanical setup, you are going for the higher magnetic field, right?
we have a mechanical setup or cryostat, and inside our cryostat we have SQUIDs, we have VTI, that is vertical temperature insert, to maintain our temperature inside the cryostat. So that's why we are getting that's why we are getting information at higher magnetic field, that how our SQUID is behaving at higher magnetic fields.
And one more question, like, do you know, is there any effect of the background on these plots?
Yeah, I think so, because we observe, you can see that we observe some noise here also, and some
Mhm.
noise here also in the
So
spectrum.
these noises are from the mechanical setup, right?
Yeah.
And what about the effect of the background?
Effect of the background. What do you mean by the background?
I mean background from the cosmics or something else or some other things. I mean,
No, there is no. We have
you don't have any effect on these cups.
no.
Okay, thank you.
Great. So Shiva, maybe you can take us to the quiz.
Yep.
Which I
So let me
I
put the link of the quiz in the chat so you all can take it.
thank you. So for those, do you want to explain to everybody why we're doing the quiz?
Yep.
Yeah.
So the quiz is based on questions from the research paper that we shared, and if you like answer all the questions, then you get a book prize, which I haven't read, but I would love to see what book this would be. But it will be a great book. So you all can take this quiz, and yep.
Just to add that this quiz prize will be given only to WMU students. I mean, everybody, you can participate, and if you were probably the highest, we will definitely felicitate that through our feelings, but will not be able to give you the gift because it is just limited to WMU students.
Yep. We do not have any partnership with FedEx right now, so won't be able to.
Yeah.
So should I also can participate? Can I also
I mean,
participate?
you only made the questions,
Yes, yes.
so you already know all the answers.
Okay.
You can tell us answer.
Yeah.
Yeah, and then we all will get 100% marks.
Oh man, who was setting this question? Okay, Shiva, you let us know when.
So we can wait for like 1 more minute. All right, so 10 more seconds we have for this quiz. If you haven't submitted it, you can submit. All right, I believe all have submitted their responses. Let me see who has. Okay, so can I name our committee members as winners?
No, no.
Then we have many candidates for this.
Just say everybody's name who has highest values,
Mm,
irrespective of they being committee member or not.
No,
So we
no.
have
Let's start with the winner first.
okay. So someone who is not from the committee, we have Dev, and we have Vikas. They have got the highest marks. Like
So
they have
two
scored the
people.
highest. Yeah.
Okay, so we now need to toss a coin or create a random generator.
Because are you from WMU?
So Vikas is not
No,
from WMU. Yeah.
I'm
Oh,
from
he's not.
France. I'm from University of Lille, France.
Ah,
So then we don't have to toss a coin.
so Dave, you're the winner.
So yeah, Dev is the winner. Don't you want to know who scored the highest?
Yeah, I want to know.
Go ahead. Yeah.
Okay, so it's just tie between MQ and Khushi.
Oh, I
You
have
all,
a question.
yeah.
I have a question. Why didn't we have questions about squids?
Okay.
She was
Anna,
just being nice, you know. She was like, if somebody read the paper, let them go easy with that.
Yes, because I thought that the question should be from the paper, not from my work, so it's better to keep the question from the paper.
okay, I also have a question. Like the relative speed, because as far as I maybe investigated, I heard that axons, like dark matter in general, it has to keep the galaxies moving at the right acceleration, otherwise things
Yeah,
will not work. And so the idea is that they should be moving relatively slow, right?
Yeah.
And so what's that relative slowness?
Can you please repeat your question?
My question is on the second question. What
Yeah. I
what
got that it's your on your second question about the relative speed. So what do you want to ask?
Yeah, like what's that relative speed? Like is the Earth moving faster than axons, or are axons moving faster than the Earth?
No, I think in that paper it is defined that relative speed is in natural units and it is relative to the galactic. Uh, sorry, I have to see the paper.
Okay.
Mm,
Okay.
yeah,
We'll find that out later. Okay.
yeah.
I was just curious to know
No,
because
no.
okay.
Okay. Yeah, but I have to find on the paper. because I took it from the paper that is the velocity of the Earth relative to the galactic axion-like particles.
So are exons moving faster or is the Earth moving faster?
I thought Earth.
Yeah,
Earth is moving faster.
yeah.
Okay. That would make sense.
So exons
Alright.
are like heavier than the Earth. How is it possible?
No, those are
No.
super tiny. They have mass 10 raised to minus 11 times the mass of
Yes.
electron. So
Yep.
it cannot be heavier than Earth. But it's just that they are moving so slower.
Yeah, but these are all theoretical things. I think Anam
Yeah.
will tell us the news maybe a year from now whether exons exist or not. Okay, Shiva, I'll give it to you to.
Can I share one interesting news that I just heard before an hour or so? That there is a physics problem called Riemann hypothesis, which was unsolved for the last 161 years. And the Clay Mathematics Institute of Cambridge has declared a mathematical physicist who is from India, Dr. Kumar Aishwaran, as the person who has solved it just recently. That was the physics news that I heard and thought of sharing with all of you.
Interesting. They've solved the Riemann hypothesis.
Yes, that's what it says.
Oh, okay. This is very big news. This is very big news.
Yeah, exactly. Like I remember you were talking about it before some time, right?
Yeah, I read extensively about it sometime when I was bored in my undergrad.
Cool. So then maybe
Yeah.
you will be able to understand this guy's mathematical explanation.
It's probably beyond my pay grade, but yeah, yeah, actually it's a math problem, but it has physics implications. Yeah. Well, Shiva, do you wanna?
All right. Okay. So we want to thank Anam who gave her precious time for our Physics General Club talk, and we would like to have you like back for another talk if you want. And also thanks to all of the participants that you also gave your precious time and continue supporting us. And we also have our YouTube page now. You can also subscribe to our YouTube page, so you can watch all the videos there. And at the end, we have the student opportunities, which will be presented by Abby. So, yep. So Abby, you can go on and you can share a screen. Okay, so Abby, you're muted right now, so you need to.
So, Shiva sent me earlier in this month this remote experience for young engineers and scientists thing. It just seems to be like a lot of different talks, which gives overviews in various STEM fields. One workshop will be like a Python and STEM workshop, which I think is pretty interesting to me personally, and I don't know about other people. And that'll be happening from today until July 23rd. And you can, I think you can still register for that. And then, yeah, then there's the graduate student research grant, which there's a fall deadline of October 28th, as always, and the graduate student virtual conference grant. And again, that'll be due October 28th if you're interested in that. I think Kushi has gotten the research grant, so if anyone's interested in that. This is one that just came today in my email, but the Journal of Research in Science, Mathematics, Technology, and Technology Education is doing a special graduate research issue. So paper topics will be accepted by August 1st, and then the papers need to be submitted by March 2022. And then I just wanted to put out there the Graduate Student Teaching Intensive is happening from July 28th to July 30th, and you need to be nominated by July 15th. I did it last year. You can self-nominate, or you can have someone else nominate you. And it's good to get in early because if you're interested, because last year I waited till the last minute and they ended up closing the thing because there was too many people, and then I ended up having to email them and they let me do it anyway, which was weird. But yeah, it's a good program. It's through Teams, and you discuss like all the different things that may be facing your students, and also like active learning strategies if you're a teaching assistant. So thank you for coming to the talk, and I hope to see you guys all next month and also next school year. So
All right, thanks a lot, Abby, for the student opportunities.